Hi everyone, my name is Katharine Donahue and I am a senior biochemistry student at Quinnipiac University. And this past year I worked with a faculty member, Dr. Alex Hodges, on a research project involving the polymerization rate of rabbit skeletal muscle actin. So actin is a critical protein that is involved in many cell functions, including cell shape determination, cell motility, muscle contraction, as well as many other cell processes. A key property of actin that allows it to participate in such cell functions is its ability to transition between a globular or monomeric form to a filamentous or polymeric form. Therefore, actin polymerization is an area of interest. Previous polymerization assays have been developed using total internal reflection fluorescence, or TIRF microscopy. These assays have also used inactivated N-ethyl malamide myosin, or NEM myosin, as a method of attaching the actin to the flow cell for imaging. Our goal this year was to develop a polymerization assay for different concentrations of rabbit skeletal muscle actin. So we prepared globular rabbit skeletal muscle actin and performed a Bradford assay in order to determine the exact concentration of actin we were using. The actin we were given and that we prepared, its original concentration was 1 milligram per milliliter, but during the preparation we did have to spin it down, so some of the protein may have denatured and affected the concentration. As you can see from Figure 2, our Bradford assay standard curve, and Table 1, we determined that the actual concentration of actin that we were using in the assays was about 0.21 milligrams per milliliter. If you look at Figure 1 on the bottom left, it shows the polymerization process of the rabbit skeletal muscle actin at different time points during the assay. Figure 1a shows the 0.21 milligram per milliliter actin's polymerization progress after about a minute of the assay, while Figure 1b shows the actin after about 2 minutes of the assay. As you can see, the assay showed to be effective and the actin successfully polymerized. We then performed the polymerization assay using the prepared monomeric actin and adjusted the concentration of NEM myosin that was used to attach the actin to the flow cell of the cover slide. This was in order to get the optimal density of actin because we're going to have to image individual filaments. We wanted the density to be enough that we could see the filaments, but not too dense that it was too difficult to pick out individual filaments. Figure 3 shows the polymerized actin using different concentrations of NEM myosin. Figure 3a shows the polymerized F-actin using a 0.01 milligram per milliliter NEM myosin solution. The actin here is still pretty dense and would be pretty hard to analyze, so further dilutions of the NEM myosin were made, and it was ultimately decided that a 50x dilution, which is a 0.002 milligram per milliliter solution of NEM myosin, allowed for the optimal actin density for analysis. And this 0.002 solution is shown in Figure 3b. We finally moved on to measuring the polymerization rates of different concentrations of actin. Our data showed that as the concentration of actin increased, the polymerization rate increased as well, as shown in Figure 4. Future prospects include measuring the polymerization rates of different concentrations of actin to further support our data. A second order rate constant and critical concentration for the G-actin are to be obtained as well. And the ultimate goal of this project is to apply the polymerization assay to archaeal actin to analyze any trends in polymerization rates.